This is going to be an overview of directed energy in a large context, not simply in the Starshot context, but in a much broader context in many, many different areas. The thing I want to emphasize, given that I have two of my contract monitors in the room here, in addition to Pete Warden from Breakthrough, is I want to acknowledge the support from NASA, which actually goes back to 2009 through Space Grant, and then started in 2014, proposal to NIAC. We've now had 6 grants from NASA in directed energy related areas with UCSB and our collaborators. And then we just are coming off of a 2-year directed energy for lunar environments through the Luster program. So NASA's been very generous with us. I also want to acknowledge Sunny White, who's somewhere here, Sunny White from Limitless Space, who has been very generous towards us, and we are now in a second grant program with them. I also want to acknowledge in a very special way Breakthrough Foundation and initiatives. Pete Warden and I ran into each other literally on October 31st, 2015 at May's 100-year Starship, which was held in Santa Clara, as I recall, so not very far from here. And someone said, hey, there's Pete Warden, you should go talk to him because he likes interesting ideas. And he was running out of the room. I thought he was head of NASA Ames at the time, which I don't think you were, but I think you were already transitioned.
I had just been fired.
You've been fired, yes. We'll talk about that later in private. And so he's running out of the room, and he said, send me something. I happen to be writing a paper called The Roadmap to Interstellar Flight, which was a kind of a summary of our NIAC program. So I sent it to him. We arranged to meet on a trip he is coming from Japan, which was quite tiring, as I recall. We had a discussion in, I think, October 2015. And then he asked if he could send it to a friend of his, who I didn't know, but turned out to be our sponsor. And that's what kicked things off. And then we had this wonderful set of meetings. So what I want to say in public is that I appreciated the incredible just vision that you had, Pete, in being open to this kind of idea that one could transform humanity. And Yuri for his just embracing of this would really change humanity. Now, whether we can afford to do it right now, that's a different issue. But just, I think the initial embracing of this as a path forward, I will never forget. So. Okay, if you're interested in the nitty-gritty details, we write lots of papers. We now have over 500 papers written, mostly on cosmology, so you probably don't want to read those, but we have almost 100 now on directed energy. So if you want to see it, go to our website. If you want to run a mission analysis, which I'll show you in a moment for Avatar, go ahead and run it. And we just published a book, a 2-volume book, which is, I'll show you a picture of it, just awful. So don't bother reading it unless you can't go to sleep. Okay, so is Interstellar feasible? We really want to do something extraordinary, but unfortunately reality kind of sucks, right? It's just, the laws of physics are just not what we'd like them to be. We really have to understand, if we're going to use our current knowledge of physics, what the physical reality is. So I'll talk about that in some detail. You also have to understand the limits of chemical ion engines, which sound really good and they are very useful. Even nuclear, which sounds like it's the solution to everything, but it turns out in relativistic flight, nuclear is extremely difficult to get to work because of the low energy yield per nucleon. Solar sails, they don't do it. Laser sails do. So these don't work for relativistic flight. And what we really want, this is what I really want, is a warp button. I just want to push it, be gone and come back, but you can't. The laws of physics don't allow you to do that. Not the warp necessarily, but you can't come back. So this is one thing. You can't go back to where you were in terms of space-time. You go back in space, but not in time. So these harsh realities push us into a very tight corner, but there is a path forward, but it's not like in the movies. And I'll show you that path, what we've done in the laboratory. I'll show you where we are in terms of cutting metal, which we are now cutting metal and making arrays. One thing to ponder for those of you that may not be physicists is that there is no clock as you go at the speed of light, which we don't know how to get something physical at the speed of light that has rest mass, but a photon has no clock. So the faster you go, the faster you get to anywhere in the universe. And the limit of the speed of light, you can go anywhere in 0 time. So it's important to understand this when you're thinking about interstellar. Okay, we have a roadmap. We're not stuck in any one place. We have this long-term vision, which will probably encompass many, many, many decades. We're starting down here with small laboratory testing, outside testing, and doing all kinds of technological things like things you just love to do, beacon locking, directed energy phased array atmospheric testing. I'm sure everybody here wants to do that, yes? Okay. But there are things like sending power from Earth to LEO and to GEO, which we can now do. You can do station keeping on orbit. For example, I don't know if you know that the International Space Station requires refueling every once in a while to keep it from being dragged down and crashing into the Earth. Long-range power beaming, Earth to moon to moon, point to point, lots of things. We just came off a NASA program now, which is a lunar program. Fast solar system missions, which I'll show you in a moment, and then eventually going out of the solar system to another one. There are technological issues from lasers, laser photovoltaics. In some missions, you'll see fiber amplifiers, semiconductor amplifiers, spacecraft, thin film reflectors, et cetera. There's a whole mishmash of things going on here, and you'll get to see some of that. All I can say at the moment is things are actually working in the laboratory. We've shown we can build arrays out to at least 50 kilometers in diameter, which is much bigger than you need for the entry missions. It's almost big enough for Avatar, by the way. And things are phase locking well in the laboratory. So that's important. If you want to be really bored, read this book, okay? If you like mathematics or can't sleep, read it. It's 700 pages, 720 pages of just mathematics, plots, and boring stuff like that. But it's kind of important. So if you like terrible novels, like a Stephen King novel, go for that. You like Stephen King? Yes, okay. No, it's terrifying. Okay, so this path forward, just in this artist's rendition, is something like you take a gigantic flashlight and you shine it on a reflector, in this case, and you go to the stars, or you shine it on a photoconverter, which powers an ion engine, and you get to Mars in 30 days with humans. And you stop, by the way, too. Okay, you don't have to pay extra for that. Well, you kind of do, but. All right, so the answer is literally what you see in your eyes. Okay, so look at this one. Do nothing else, you want to go sleep after this slide, okay? We were contacted by the Avatar team who said, we read your papers, we added a laser sail to our mission design, which was news to me. I said, okay, fine, I can do that. I need to know something about your mission. What's the mass of your spacecraft? We don't know. Okay, that's not really helpful. How many people on board? Oh, that we do know, 200 people plus 25 for crew. Okay, fine. So I made up an estimate. I said 1,000-ton ship. That's about the minimum I can imagine, 4 tons per person. Okay, seemed reasonable to me. 7 years to Pandora, which is in the Alpha Centauri region. All right, here's a little picture from their website. Now, watch the numbers. I'm a numbers guy. Could have been a bookie in another life. Instead, I'm a physicist, all right? Who would have known? All right, so this thing called the ISV, Interstellar Vehicle Venture Star, is the Avatar spacecraft, okay? So math is optional and annoying for filmmakers, I suppose. Laser-driven is their primary sense of means of propulsion, with antimatter and fusion thrown in, okay, because you got to have other things on board to make it look cool. Read our papers. Well, no one does. All right, at that speed, at 70% speed of light, you have about 9 megatons per kilogram. So 1 kilogram thrown at 0.7 C is 9 megatons. That's not quite the largest nuclear weapon that we've ever detonated in the US, but it's getting close. All right, on the other hand, that means that the mission would be 9 teratons of kinetic energy, 9 trillion tons, okay? Just let it sink in, 9 teratons. The KT extinction, the 10-kilometer asteroid hit the Earth, was about 50 teratons. So we could make a planet killer, right? So you want to go to interstellar war? We can do it, right? We just don't tell the spacecraft to slow down and stop, just hit, right? So kind of ponder that. All right, so we ran an analysis again for them, and we came up with, well, I don't want it to be as big as the Earth or as big as the Death Star in Star Wars, so I made it 100 kilometers. Yeah, I lived in Los Angeles. Let's just get rid of Los Angeles and replace it with an array. Good idea, okay? So how much power do you need? Well, 10 petawatts, okay, P. So there's giga, tera, peta, all right? So 10 petawatts is what you need. You get a sail diameter of about 36 kilometers, assuming 1 micron thick, 112 kilometers for a 10th micron thick, like Harry described this morning. Think about it though, 10 petawatts is 1/10 of a kilogram per second of matter annihilation, or 3.3 million kilograms of matter antimatter annihilation per year, or 2.5 megatons per second. So how many of you like to build nuclear weapons? Anybody in the room? Okay, 2.5 megatons is larger than the typical ICBM thermonuclear weapon that we have, which is about 10 times less than that. You need about 25 ICBM equivalent thermonuclear weapons per second, okay, to power. Yeah, good, thank you. Finally, someone gets it, right? I really appreciate it. I teach for a living, and when I get someone who's not on their cell phone or falling asleep who laughs, it's great. Thank you so much. I'll pay you afterwards, okay? All right, 10 petawatts is also 1,000 times the world's electrical production. Okay, not a problem. I'm actually not saying this is a problem. I just want to point out the reality. If we cover the entire moon in PV at 100% efficiency, we get 13 petawatts. So it's not crazy, okay? It's not something humanity couldn't do, but this is the number, okay? So you can't get around this. Well, at least I don't know how to. So think about it. This is 3,300 tons of matter antimatter annihilation per year, and they wanted, I said 1,000-ton spacecraft, so the matter antimatter annihilation is greater than the mass of spacecraft. Okay, so they didn't do the math, right? Obviously, they called me, hey, you write all these stupid papers with nothing but math in them. You do it. Well, I did it. Okay, and you might say, well, can't we just use matter antimatter annihilation? The answer is no. That's not better than directed energy. It's worse, because you only get 1 photon going out versus 1 coming in and bouncing off. You actually get twice the momentum transfer with directed energy. So whatever, you're in serious trouble. But it's a movie, so whatever. Okay, so I got them up to 66% the speed of light, or 80% with a 0.1 micron thick sail, like, where is he? Where's Harry? Harry, okay, so we need a 100 kilometer 0.1 micron sail. Okay, can you do it? Aha, yes, okay, thank you. All right, fine, okay. But the good news for Harry is it's only 10 megawatts per square meter, so important to think about. Larger missions have lower flux on the sail for the same engine, launch engine. Lower flux, easier. Bigger is easier, smaller is harder. And you don't need very much in this case, 99% reflectivity, 0.1% absorption, the sail runs at 172 Kelvin. Okay, and you get about 17% launch efficiency when you include relativity, okay? This is another good one. How much electricity does it take to launch? I assumed 100% efficiency. It takes 63 gigawatt hours, or 6.3 petadollars at 10 cents a kilowatt hour. Reasonable, yes? Yes, come on, reasonable. Okay. All right, for reference, the US GDP is about 30 teradollars, so you need about 200 plus years of US GDP just to pay the electric bill. Okay, for another reference, the Saturn V is about 50 gigawatts at takeoff, so you need 200,000 Saturn Vs constantly for about a year. Option, use unobtainium. That's why you go to Pandora, get unobtainium, yes? Okay, the other one is go slower, duh, okay, much better. But the really good one is start with small mass missions, like Starshot, okay? And the launch cost goes roughly as the mass of the mission for the same speed. The gamma minus 1 goes to v squared over 2 in the non-relativistic limit. So for example, 1 gram, like we're talking about for Starshot, going out at 0.2 C is 10 to the minus 10 times lower, 10 billion times lower cost per launch, or $500,000 a launch. Okay, that's reasonable. This is where you start. Maybe this is where we should start, okay? I mean, this is just numbers, okay? I'm sorry. I can't do anything about the numbers, right? They're numbers. If you want to run your own mission analysis, go to our website and get all this crap out of it and, you know, knock yourself out. What did I get? Oh, I got 10, we'll do 1 gigabit per second coming down. So we can do a full-blown If Cox goes to 10 gigabits per second, we could do 10. Okay, but right now I did it with 1. Okay. All right, so let's go on. This is a picture. We did some graphics, our own, and then we made a little movie. So here's the light sail, and here's a laser you can see shining on it. I'm not gonna go super fast, yes, I know. And we're pushing it, but you're not pushing with much pressure, so it doesn't collapse. And then you finally come around, and here's the spacecraft. Okay, this little thing here. Okay, 1,000 tons, whatever. I told them, you're not gonna like it, but they didn't believe me. These are shields for radiation, which, as we heard, is an issue. All right, this comes from our proposal NASA in 2013 and 14. This is a phased array. So this is how you actually make the big flashlight. You don't make a gigantic single flashlight, you make a bunch of little flashlights and phase them together, critical. And then you have a Fourier transform device that you change the phase and the amplitude, and you can write, breakthrough is here on the moon. Literally, you can melt the surface of the moon and write it, yes? Okay. Okay, phase controllers, all kinds of glue. I'll show you that from our laboratory. This is what we're working at the moment. It's a 1 meter demonstrator. This will reach LEO. Oops, sorry about that. This will reach LEO for sending power to LEO objects. Okay, so just lots of other things from our papers. Here's a 1 gram payload. Here's a 1 kilogram payload, like a CubeSat, and here's 100 kilograms, kind of like a new Voyager. Speed on the y-axis here is a function of array size from 1 meter to 10 kilometers, different densities here. Answer, you can get to the speeds you want without killing yourself. Still really, really hard, but you can do it with gram or even kilogram class stuff. It gets really hard when you get bigger than that, but you can do it. You want to get pizza to Mars? Okay, someone said pizza to Mars in 60 days. Forget it. Get pizza to Mars in 8 hours. Okay, we can keep it warm. Okay, or you can get it to the moon in an hour. That's not so bad. So Amazon might be interested in this. Okay, NASA has to look at the following. Can we get humans to Mars faster? So we said yes, and we came up with the following. We get humans to Mars in about 30 days, including landing, with a 100-ton launch and 15 tons delivered to Mars. We can also get you out to the outer solar system. So this is from a paper. There's lots of papers listed here. Just go to our website and you'll find lots of them. It's entitled Fast Solar System Missions. But you're not using momentum transfer. You are using the light, the energy in a photon to convert it to electrical energy and driving an ion engine. So if you want to go fast in the solar system, don't use momentum transfer unless you want to go relativistic in the solar system. Go to an ion engine. So I'll note the following. A CubeSat only takes an array 10 meters in diameter, not that big, and only 1 megawatt. Gets you up to close to 100 kilometers per second at the peak, and then you keep going. So this is not crazy. Well, at least by my standards. Okay, so here we are here. We'd like to be here in, say, 10 years with maybe 10 to 30 meter class systems, and then eventually, I would say, 30 to 50, maybe we'd like to be out at Interstellar. Okay, we're cutting metal, literally. So this is not CGI, this is not a plot, this is a person, this is CGI, okay, this is metal. The trick is to take the target, which has a beacon on it, which I showed you, and then phase invert the system so you get an adaptive optics system like you do in astronomy, except in a much more complex way. So this is the phase solution that we presented back in 2016 and 2017. I don't think anybody understood it. It's a nested tree phase convergence algorithm, and it works very, very well. Okay, so these are some drawings of what we're currently building. This is CGI, but you'll see the real thing in a moment. It's about the size of your hand and about the length of your arm, and it's at full scale. You make as many as you want, you get as much as you want on the target. It's at full scale. Okay, this is what they look like on the table. Lots of fibers and connectors and stuff. We do a lot of work in our lab. We've published lots of papers with power spectrum that bore the crap out of people, but that's what we do for a living. Okay, so if you push play here, you'll see the beacon on when it's phase locking, beacon off when it's going out of lock. So we've been able to phase lock just fine in the lab. We also can introduce things like atmospheric perturbations by using a deformable mirror, by using a deformable mirror to introduce perturbations as they would be in the atmosphere. And then we run our system and see, can we take them out? And the answer is yes, we can. It works, and it works in about 10 microseconds. We can pull out the atmospheric perturbations. So if you play these two movies, this one is atmospheric, sorry about that, atmosphere unlocked with the beacon unlocked, and this is locked. And you'll see locked, even in the presence of pretty severe atmospheric perturbations, the system converges. Okay. We make little spacecraft. They're not as beautiful as what Harry showed you. These, on the other hand, are, sorry, Harry, real. Anyway, whatever. So a little different approach. But you can put about 1 trillion transistors on this, which is of order, 1,000 high-end Pentiums at the moment. If you want to read a cost analysis paper, my only foray into economics, read the Economics of Interstellar Flight, another paper on our website, and you can solve your own optimization problem for economics. Turns out that the cost of the optics is about 1/3 in the optimum solution. The cost of photonics is about 2/3. Okay, I know I got to get out of here. I get it. I'm going. You can yank me off. I know. I see it. You're threatening me. I get it. All right. This is what we're building with some money from a couple of our contributors. And we should have this in about 2 years, be my guess. So this is a person, by the way, taller than me, okay? All right. If you want to know what would you do with the big flashlight, if you were another civilization, you wanted to tell them that you're here, read this paper, which is the Search for Directed Intelligence, which talks about it. You can get out to Z of 20. If you want to send non-humans, we have another paper on that. You can send tardigrades, much better, by the way. Humans, we're high maintenance, high mass, and really not very good for interstellar travel. These guys are radiation hardened and they can exist in a vacuum. No food, vacuum, okay? We woke them up, by the way, after 40,000 years, and they come alive. Okay, if you want to defend the planet, you can do that. Read our papers. If you want to do power on the moon to a rover, we're just finishing up a program here. This is our phase 2. Do that. Okay, it's not a one-trick pony. This system allows you to do lots and lots of things. So here's some pretty pictures. All right, we'll finish up here. It's a path forward. If you want to go relativistic, it's the only real path I know of at the moment. Even antimatter is highly problematic. It's also a path to high-speed spacecraft, including high-mass missions, including humans to Mars, et cetera. It does lots of other things, and it leverages this huge industry we have that we like with our phones, et cetera. But this leverage, by the way, is much, much greater than the NASA budget per year. Okay, and students love it. Okay, why they love it? Because they bring their cell phones from their friends in and they blow holes through it. Okay, they love it. It works great. Anyway, it's a really good thing for students and public. Okay, I'll stop.